Well, welcome back everybody to Tech Days Online. We're coming to you live from Future Decoded at the Excel Centre in London. We've just finished our morning keynote sessions here, and out in the expo area here at the event, we've got our people and our attendees thronging around our various exhibitions here. The keynotes this morning, we've had Joseph Chiros, one of our corporate vice presidents, talking about intelligence and data. We've had presentations and discussions around things like intelligent agents and bots, and the ability to augment our senses. And we also had our other keynote speaker as our guest here for this session today, Katja Hofmann, who's a researcher at Microsoft Research in Cambridge. Katja, thank you for coming.
Thank you.
Do you want to give us a little bit of background to yourself? How did you end up working at Microsoft Research?
Sure. It's a long story. I started coding when I was a kid, and I've always enjoyed this kind of creativity and this freedom of being able to invent things and just make them happen. It took a while for me to realize that in AI research that would be the space where I could make the most out of this. But now it's really exciting to actually work in AI research and invent the future.
So this morning on stage you gave a great presentation to about 5,000 people here today, talking about interactive machine learning. So I've heard of machine learning, I've heard of deep machine learning. What's interactive machine learning? How does that differ?
So interactive machine learning is what I see as the next big challenge in artificial intelligence. At the moment we have systems that in a way replicate slices of intelligence. So for example, we have machines that can see, we have systems that recognize objects at the level of human level accuracy, or that recognize human speech and translate it to other languages. But what we're aiming for are systems that can make sense of their environment end-to-end, and then can figure out how to achieve goals in complex environments. For that, we need this element of interactivity. We need to have a system that can take in information about the current state of the world, about what's currently going on, make sense of that information, and then decide on a plan to take action. And then it needs to be able to learn about the consequences of its actions. So if something goes wrong, if it makes a mistake, it needs to be able to figure out what went wrong and improve its behavior as quickly as possible.
Okay. So, and this morning in your talk, and we'll run through that in just a second, you gave, essentially you're using Minecraft as a way of exploring this interactive machine learning. So do you want to just take us quickly through some of your content from this morning?
Sure. Absolutely. So I started the talk in the morning just looking back at how far we've come in the field of artificial intelligence. Only 65 years ago, computing was in its infancy, and Turing was really a pioneer in this area in thinking about future possibilities and asking these really deep questions. Can machines think? Can we build machines that have certain human abilities? So in those 65 years since then, we have built machines that replicate some of the human abilities, like I mentioned, learning to see. So now we have software in every single mobile phone that wouldn't necessarily know that this is a picture of my team, but they would be able to detect that there are faces in there, and the apps are already using this technology to create memorable snapshots of their family.
We also have a site called What Dog, I believe, Microsoft Research, which essentially does the framing of the very attractive faces you have in your team here. We also can do that in terms of looking at pictures of dogs and identifying breeds. So irrespective of faces, dogs, it's all about identification of objects and features inside images. Right?
Exactly. Okay. It's really recognizing patterns in large amounts of data, be that images or be that speech, for example. Yeah. And now we have roughly solved this challenge of recognizing those patterns in very complex high-dimensional data. But what's still missing is how do you actually react to what you see? How do you react to what you see in the data? And at the moment, this behavior is hard-coded. We do not have systems in the real world that kind of explore what they should be doing in a certain situation and how to improve their own behavior.
So yesterday, Chris Bishop, who's head of your lab in Cambridge, he gave a presentation in the morning, and including that was a demonstration of live translation from English into 4 languages and back. So we had Russian, we had Chinese, I think we had English and French and German. So, and I understand we're almost at human translator levels of accuracy now. Would that work?
We're definitely at the level of human level speech recognition. And in fact, Microsoft Research published the results last month, demonstrating that they were equivalent to human level accuracy on this switchboard benchmark for English. A translation, I think, we're still not at the level. There are challenges in, for example, understanding long-term dependencies within a sentence, really getting to the meaning of a sentence. So really, this problem of making sense of the world, this is something where we're still far behind humans.
Understood. Okay. Thank you.
So then I went on to kind of look back at this question of what is intelligence, what are we trying to achieve? And one definition that I like is from Shane Legg and Marcus Hutter, who formulated based on, I think, about 70 responses that they had gotten from diverse set of researchers, and condensed this into this very short definition of intelligence measures an agent's ability to achieve goals in a wide range of environments. So the keys here are really achieving goals, so making sense of the world and figuring out what to do, in this wide variety of environments. We don't just want a system that's specifically tuned to being able to walk to the door in this particular room, but we want to have agents that figure out how to navigate any kind of 3D environment, just like we are able to do.
And it's important to know that this definition of intelligence, the issue of the definition of the word, is really important, isn't it? Because we talk a lot about can systems be intelligent? What does that mean? It very much depends on how you think about what intelligence is.
Right. Yeah. So if we want to make progress in a research area, especially something as empirical as AI, we need to be able to specify what we're trying to do and measure progress in this direction. And there's no kind of uniquely accepted definition of intelligence, so there is a lot of discussion on what it actually is that we're trying to do. But we can build this up. We can say, okay, this is the best we have at the moment. This is the best thing that we can measure at the moment, and then that allows us to bootstrap and make progress in the right direction.
Very good.
So now what's fascinating is that we can actually use existing computer games to make progress in artificial intelligence research. If we look at those key components of achieving goals and interacting with complex environments, then it turns out that Minecraft is a fascinating fit for enabling rapid progress in AI. As I mentioned, AI is a really empirical discipline, so it's key to be able to experiment very quickly, to try out a new idea, see if it works, and then make progress very rapidly. So by building on the huge variety of environments and settings and tasks that you can build in Minecraft, this allows us to really bootstrap from that. So if we look at what we get out of Minecraft, first we get huge amounts of data, and we get this ability to run experiments quickly at scale and in a repeatable manner, and that is something that is shared by video games. But what's unique to Minecraft is that it's this sandbox game, it's this open-ended world where people do all kinds of crazy things. You don't play it along a fixed storyline, but rather you're put in this world and you interact with it. And people go on adventures, they create mini games for their friends, they interact socially, they do amazing construction projects, they explore their creativity. And this open-ended nature is what makes it such a fascinating fit for AI, because what we're really trying to develop are those agents that are put in this environment, make sense of it, and figure out what to do. So that matches this really, really nicely. I'm so convinced that this is the right way to go that my team and I developed this platform for AI experimentation, Project Malmo, that we open sourced earlier this summer. So everyone can now go and try this out and explore some of the technology that is already developed. And I'm hoping that it will also inspire the next generation of AI research.
Okay, very good. So can you tell us a little bit about, obviously Project Malmo is available on GitHub, it's open source. So can you give us a little bit of insight into actually what it is, how it's built, and what you can do with it?
Absolutely. On a very high level, this kind of schematic that I like to show people is that the Project Malmo platform consists of a mod that hooks into the game Minecraft and that exposes information about the state of the world. And it connects to an API. And this API is kind of the layer between the game and the actual user code. So a user would hook into this API to get information about the world to the agent that they're developing. And then the agent would decide what to do, and that is translated into commands of what to do within the Minecraft game. So you really implement this interactive loop between the game and the agent.
So essentially it's a coding environment to enable muggles like myself to actually explore and play with intelligent agents in the world, the dynamic world of Minecraft that you can create.
Exactly.
Okay, all right. So what does the code look like?
A very simple example is this kind of 101, my first Minecraft Malmo agent. And the key bit here really is this loop where a mission is running, the agent observes some information about the state of the world, and then it can react to it. Now in this first simple example, it's just ignoring the state of the world, and we just tell it to move, turn, and jump. And we can look at it and we get an agent that actually moves, turns, and jumps in this entirely flat world.
So essentially, with Inside Malmo, this is your hello world example. Basically, it's your agent doing basic moves, no intelligence, but it's just essentially being able to take some data out of the world in terms of state, and essentially have the agent move within that world. So that's the base level integration.
Exactly,
Okay,
exactly.
so where do you go from there?
So the next thing you need in order to actually set up an experiment is an actual task for the agent. And we have developed something called the mission XML format, which is an interchangeable XML format where you define what kinds of elements you want in the environment, but also information about the goal, or for example, what kinds of rewards the agent should receive.
Okay.
So we see a kind of abridged example over here where we create a classic reinforcement learning task, the so-called cliff walking task, where the aim is to get the agent to learn to navigate to the goal in the package.
So just pause there. So you're saying a classic reinforcement learning task, which is some poor soul having to navigate along a cliff without falling off and being eaten by lions or drowning in sharks or something like this. Okay. In this case, it looks like lava. Right?
Exactly. So
Okay.
we use lava.
Okay.
And it's this textbook example of the. It's the starting point for someone doing research in reinforcement learning.
Okay.
Is to read the Sutton and Bartow book, and the cliff walking task is one of the classic examples there.
Okay. Very good. And so, is it just cliff walking then that you can do with this? Are there other things?
No, so what's really fascinating here is that we have these very simple building blocks, but these give rise to a huge variety, first of all, of different tasks. So you can imagine building up from these building blocks complex navigation, climbing structures, even collaborative tasks where, for example, you have to maintain a farm together with a group of other agents, or where you have to explore the world or navigate complex parkours like we see over here.
Got it. Okay. So just to pause here for a second. So with sort of classical, can you use that expression, deep learning, it's essentially static, right? So you have a vast training set, whether that's pictures of dogs or pictures of faces or signals in data. You put it through a deep learning process, and which you train the network essentially to recognize the features that you're trying to network. So interactive machine learning isn't static though, right? So there's this dynamic. So how do you then build on deep learning with reinforcement learning?
Yeah, you're really mentioning the key point there, that with the deep learning you can extract certain patterns, you can make sense of the environment in a way, but then the actual decision is hard-coded by the system designer. So for example, in a self-driving car, you might see if you detect a pedestrian on the side of the car, then steer to the other side. But that only works in environments that are fairly predictable and fairly static. Now the key characteristic about the real world is that it's not very predictable, that it changes all the time, that unexpected things happen, and we need to have systems that are able to deal with unexpected things in a reasonable way. So they need to be able to learn about the consequences of their actions and make sense of the environment in that way.
So with Minecraft, you have the ability to create new environments safely, they're virtual,
exactly.
But with a rich set of dynamic behaviors and dynamic sort of features, and then explore how the learning agents work and adapt and essentially grow their capabilities within those environments.
Exactly. It really allows us to focus on the learning mechanisms themselves. So understand what we need to put into the agent so that it can make sense of the environment, avoid behaviors that would be unsafe. And once we understand how that works, we can start to think about moving that into real world applications.
Understood. So do you want to explain a little more?
Sure. So one of the key directions that I find fascinating is reinforcement learning, and it's really built on this idea of having an interactive loop where the agent takes an action, then it gets observations about the environment, and from learning from those interactions, it learns how to make sense of the world and what the consequences of its actions are. And we have a simple example here to just illustrate the main ideas. So this is again this classic cliff walking task that I showed earlier. And the task for the agent is to learn to navigate safely to the goal. Now, initially, the agent doesn't know anything about the world. It's just put in there, and then this is what happens.
Okay, so it takes a step, falls in the lava, falls in the lava and dies. Yeah, exactly. Yeah, it could fall in the lava. That'd be good as well.
Exactly.
Yeah.
But if we have a learning agent, it now learns from this experience. So we can look at what the agent has learned so far. Here in the middle, in this representation, we see kind of the tabular representation that the knowledge of this agent is encoded in. Every square is one of the fields in the world, and the little dots indicate whether the agent has experienced something positive or something negative when taking a step in this world. And now here you can see, as it explores more and more, it builds up this map of the environment. And after about 10 minutes of training, it has explored this environment sufficiently well to actually navigate to the goal safely without falling in lava anymore.
So does the agent itself, in any kind of tangible way, understand the idea that if it falls into lava, then it's died, or that it's a bad behavior? Is that the way the reinforcement works?
So it wouldn't understand that it's died. I mean, that is very figuratively speaking. What it observes here is a negative feedback signal. So it's a numeric reward signal, and it learns the representation of how high or low that numeric reward signal is. One thing that's interesting here is that the agent wouldn't be able to generalize this concept of lava. It really only has this representation where every square is a unique new square, and it has to learn what happens new for each one of those squares.
Okay, so it's treating each individual cliff square, each individual lava square, as an individual observation or entity. Okay, it's not generalizing. Okay.
And this question of generalization was a long-standing issue in reinforcement learning. So you know how to learn from trial and error, but how do we generalize to something that makes sense? How do we generalize this concept of lava? And this is where combining reinforcement learning with deep learning is such an exciting new direction, because deep learning allows us to extract those patterns and generalize, and reinforcement learning gives us the component that tells us how to backpropagate through the experience to learn about what will eventually happen. So here we see an example of what we're currently working on in my team. We can see an example where the agent is only observing the visual field, the image pixels, and it learns to interpret those in a way that's meaningful for taking decisions. And we can see that when it's looking at lava, it has learned that moving forward into lava has very bad consequences, so it will avoid that. And what's exciting about this demo here is that the agent has been trained end-to-end just from input of pixel images and this numeric reward signal, and it has learned how to take the right actions in order to achieve this goal of moving safely through this environment.
So this concept of generalization is really important, right? So going back to my dog example, you can show it the What Dog Network a bunch of pictures of different dogs, and classically in AI we used to try and break the image down into, say, matchsticks representing the legs and the body and so on, and try and map that to some model, and that was the classic approach. Now though, the network learns the features of the image which look like a dog or our dog, and it generalizes then so that a dog in a different pose or from a different view, it's got that sense of generalization built into where the network works.
Right, exactly. And now we're coupling this ability to generalize with a mechanism for actually making meaningful decisions in the world. Exactly.
And that generalization part is vital to dealing with uncertainty or in complex dynamic environments, right? So to interpret things that we see.
It's something that we as humans do very naturally, right? We don't think in terms of pixels in the world, we think about semantics, about the meaning of the items that we see, and we know that every time we see a cup with water, that's something we can drink from, and you know, water has this.
So comparing this to like human intelligence or biological systems, so you know, when a baby is born, it has some basic capabilities to see and to touch, and has some sensory processing, but is it the same process by which we learn when we're young in terms of reinforcement of experience, feedback we receive on those experiences, and the way it improves our behaviours? Is it a similar kind of, is it modelled on a similar kind of capability?
So the research takes a lot of inspiration from insights into how babies learn in particular. But at this point, we still don't know what exactly those crucial components are that we need to replicate. For example, some argue that we need to replicate something like an evolutionary process, and others think that there's a lot that we can already build into those systems, and that all we need to understand is the learning mechanism to build up on what we already know. It's comparable to the time before we built airplanes. We saw examples of birds flying, but we didn't know whether it was crucial to have feathers or whether there were other aspects, as it turned out, of aerodynamics that actually allowed objects that are heavier than air to take off. We're at a very similar stage in terms of AI. We kind of have a sense of what the bits and pieces are and what the crucial mechanisms will be, but we don't quite know yet how to put them together. And that's why rapid experimentation is really crucial.
I understand. That's very good. Okay, so where we've got to so far is we have deep learning. We complement that with things like deep reinforcement learning, which gives us the ability to learn, or agents' ability to learn from experience, and thereby have a way to start adapting our behavior and dealing with more complex tasks in more dynamic environments.
Right.
Okay, so what's next with this? Where are we heading with research in this? What are the research directions around this?
So one potential that I'm really excited about is this hopefully ability to develop collaborative AI agents.
Right.
So agents that can make sense of our world and what it is that we're trying to do, that are then able to help as best they can so that we can augment our abilities and achieve more.
Okay, so have you got any examples of things that potentially that you could work on in that area?
It's still very early stages, but if we look back at the example of machine translation that you mentioned earlier, humans know the meaning of a sentence, and that is a key limitation right now, that AI agents can't connect the words that they translate to something that would make sense in the physical environment. So if we could have them learn more information about what the natural world looks like, then it's possible, or it may be possible, to give them a better sense of meaning, to actually make those translations closer to what a human would understand when they hear those sentences.
So right now, in terms of the state of the art, we were talking in your presentation earlier, you talked a little bit about the application of this into things like web, for example. So what are the short-term, obviously we can get Project Malmo, we can experiment inside Minecraft, but in commercial setting, what's one of the examples of the way that this could be applied?
So one application that I'm very excited about, and that is publicly available today, is the so-called multi-role testing decision service. This is a service that was developed by our colleagues at Microsoft Research in New York, and it's the first publicly available interactive machine learning service. It's applicable to, for example, optimizing websites or generally user interactions with web applications. For example, it was used to learn what news articles to recommend to users on MSN, and it resulted in a 25% increase in click rate over a competitive human editorial baseline. It's based on a type of interactive machine learning that's called contextual bandits. Those mechanisms observe information about the world. So, for example, what articles someone looked at in the past, or what time of day it is, and then they learn a model of what kinds of articles to show to that user. Because it's in this interactive setting, those bandit algorithms have to explore. When they have a new article, they need to show it to a couple of people to understand what kinds of people are interested in reading that article. So it's an example of having to learn from trial and error, balance exploration of new articles with exploiting what it's already learned, and turn that into a system that can automatically learn how to take decisions in those environments.
And achieves a level of performance better than human editors can do?
25% better.
Yeah, okay. So augmenting and extending, in that case, some of the capabilities of the... Mm-hmm. So that's available now, that service is available now on Azure ML.
Yeah.
So we can experiment with Malmo, and we can use that directly in terms of exploring its capabilities off the Azure machine learning site. Okay, very good. So let's go to another vital sort of application area of this, which is, of course, gaming. We obviously come from Minecraft, we talk about the experiment there, but a lot of games contain increasingly non-player characters, which is said, we talk about the intelligence of the non-player characters, right? So is this applicable into broader gaming scenarios and new forms of gaming experience?
Absolutely. So I'm really excited about the application possibilities of interactive learning in a game context. At the moment, there's a lot of ingenuity going into designing video games, and they're masterfully constructed to create the sense of agency, so the sense of connection, for example, with a non-player character in a game. But what's missing is an AI agent that could interpret what you're currently trying to do. So if you think about a more open-ended game, how could an AI agent understand what your goals are and create a more meaningful, engaging experience around that?
And given multiplayer gaming scenarios, I mean, we do great work at the moment in terms of connecting thousands of players in multiplayer scenarios via the cloud. if you start connecting players and the data from those games in the cloud, you start creating a point where you can create much greater learning opportunities to extend learning of the NPC, non-player characters, right? And so could you end up in a position where a game becomes unplayable because the NPCs have learned every tactic, every strategy?
I don't see it so much as competing with humans. What I really want to move towards is develop systems that create new engaging scenarios. So you wouldn't optimize a game AI for I want to beat every human in chess, right? I mean that wouldn't be a fun experience. No one would want to play with this. But instead we need to learn how to optimize these agents for fun and engagement. So what is what would be a character in a game that makes it fun to come back to?
And I think that's the important thing, because one of the misunderstood things, or we don't really highlight it much, is that for years computer education in schools has been about teaching kids how to interact with computers. What machine learning is doing is kind of inverting that problem now, and it's like the computers, the machines, are learning how to interact with us. So where do you see that heading? I mean, one of the big things we talked to over both days of Future Decoded is intelligent assistance and the ability to have conversational interfaces. Is interactive machine learning applicable in those scenarios?
Absolutely, that's definitely where I see this area going. At the moment, it's so hard to get a computer to do what you want it to do. And it should be much easier. We should be able to just tell it, just do what I want you to do, just help me achieve this goal. And by moving in this direction of understanding natural language, but also understanding a user's goals and their environment, we are making this possible.
Okay, very good. And then, so beyond sort of improving intelligent assistance and that conversational intelligence, I guess, take a further step back to the bigger picture. So one of the big debates, certainly going on the press at the moment, is this idea that with the ability to move from static towards dynamic learning, and the fact that the agents, the network's intelligence can improve based on feedback and own experience, that you inevitably create this ability to improve intelligence. It grows its capabilities and at some point exceeds that generalized capability of humans. So we call this super intelligence, right? Do you subscribe to that view of the future in terms of AI is more capable in certain environments than we are, and the fact then that that'll inevitably lead to them becoming self-aware and blowing us up?
Right. It's a question that absolutely comes up a lot and that I find fascinating. It's important to keep in mind that in many areas, computers are already much better than humans, right? If we try to multiply 10-digit numbers, we wouldn't do that in our head. We would use a computer because it's just so much better at this. So I don't see this ability, this increase in ability in computers as competing with what we are trying to do. I see this as really complementing and augmenting what we are doing. One of the strength of humanity is that we're able to collaborate effectively and at scale. And if we are able to develop AIs that can collaborate seamlessly with us, we just extend on that ability. And just think about the opportunities for solving key problems that we currently have in the world that we cannot solve at the moment. I'm hoping that some of this collaborative AI will make that possible.
Okay, so we're not heading into Terminator scenarios here, but what we're really genuinely talking about is the ability to augment our own innate capabilities or special capabilities with artificial intelligences to extend what we can do to make us more productive.
Absolutely. And that is a crucial discussion to have right now, to understand how we harness those new abilities that we're developing to make sure that they benefit all of us.
Thank you very much. So thanks so much for your time. Really appreciate you joining us here today. We've been talking about artificial intelligence throughout the 2 days at Future Decoded. There's more content in our track sessions here this afternoon, I believe more on TechDays Online. But thank you for your insight into what is a very dynamic area. For those interested in follow-ups, what we have on the Microsoft Research site, you can find access to all the research which goes on around our Microsoft labs around the world in this area. And if you're interested and you are based in the UK, on December the 10th in the King's Cross area, some of our MVPs are running an event called AzureCraft, which is a combination of Azure and Minecraft. It's an event for parents and their kids to both explore how to set up networks with inside Minecraft, but also we're going to be using Project Malmo at that event to start kids on the journey of understanding how they program AI and how intelligence and learning can be built into the kind of skills which they're acquiring. So if you're in the UK or can be there December 10th, go on to Eventbrite, search up AzureCraft 2016 and come along to King's Cross area to see what we're doing with Malmo. But for now, thank you for being with us today. Thank you again, Katja, for your time and also on stage. And have a good rest of the day, everybody. Thank you.